Hello, everybody. Welcome to today's current seminar. Today we have one talk, one speaker. Our speaker is ZWaleed Diab. ZWaleed Diab is a fourth-year PhD student in the Chemical and Petroleum Engineering Department at Khalifa University. His research interests include machine learning for scientific computing, advanced numerical and discretization schemes, and CO2 sequestration. ZWaleed Diab is a member of the Society of Petroleum Engineering, the Society for Industrial and Applied Mathematics, and the International Association for Mathematics Geosciences. He holds a bachelor's and a master's degree in petroleum engineering from Khalifa University, Abu Dhabi, UAE. With that introduction, you can begin your presentation. Thank you for accepting our invitation to give a talk
Thanks,
today.
Thanks, Nazanin, for the nice introduction. So my name is ZWaleed Diab, and today I'll be presenting the U-DeepONet, Unit Enhanced Deep Operator Network for Geologic Carbon Sequestration. I'm a member of the research group led by Dr. Mohammed Al-Kubaisi. So we have a small research group. Our members, Dr. Mohammed Al-Kubaisi is an associate professor of chemical and petroleum engineering. Dr. Wenjuan Zhang is a postdoctoral fellow who also did his PhD with Dr. Mohammed Al-Kubaisi. His main interest is in advanced discretization schemes, and recently he picked up machine learning. I'm mainly interested in machine learning for scientific computing, and my colleague Omar Chaabi is interested in multi-scale methods for PTEs. So the outline for today's talk is first we're gonna introduce the problem of geological CO2 sequestration, and we'll then highlight the challenges in numerical simulation and why we will resort to surrogate models using machine learning. Then we will discuss the problem setup and the data set we used for the U-DeepONet. Then we'll discuss some of the neural operator and some of the more popular ones and that inspired the U-DeepONet architecture. Then we'll look at the results and some benchmarks and comparisons with other architectures for the same problem. And then we will conclude this talk. So the problem of geologic CO2 sequestration is mainly important for addressing the climate change problem. And as you may know, that the global temperature has been rising for the past few decades. In fact, it's estimated that it has risen about 1 to 2 degrees since the start of the recording in 1850. And it's mainly due to the anthropogenic CO2 that humans emit into the atmosphere. There are billions of CO2 metric tons emitted into the atmosphere globally every year. And although some of this CO2 is being cycled through the carbon cycle, most of it is being accumulated into the atmosphere, which contributes to the increasing amounts of greenhouse gases in the atmosphere. And as you may know, the greenhouse gases are the main culprits in global warming and probably climate change. So CO2 sequestration tries to address this problem by trying to remove the CO2 from the atmosphere and put it back where it belongs in the underground. So we usually try to collect the CO2 from high concentration areas, probably near factories, transport it to the storage locations, and then store it underground into suitable and well-picked locations such as deep saline aquifers, depleted oil and gas fields, and unminable coal seams. These locations are usually chosen for capacity, injectivity, and most importantly, for their long-term retention attributes. The idea being that we want to store this CO2 underground for as long a period of time as possible. This is mainly a problem that we refer to as the storage security problem. So we want to make sure that the CO2 that we store underground stays there for thousands of years and hopefully forever. We don't want it to escape back into the atmosphere. It obviously defeats the purpose. So the problem of storage security depends mainly on the storage site selection. We need to select a suitable storage site and a good reservoir to store it in. We need to monitor the storage, and we need to manage the site where we store the CO2. The way we monitor and manage the reservoir usually is through some direct methods such as seismic surveys and wellbore monitoring and maybe well logs. In this way, we can collect data directly from the reservoir underground, and some indirect methods such as the reservoir simulation, where reservoir simulation offers us a forward-looking approach. And this approach allows us to understand the subsurface and the way that the CO2 plume is migrating underground, the various physical phenomena such as dissolution and mineralization, which mainly trap the CO2 for underground for a very long period of time. At the same time, reservoir simulation allows us to not only monitor CO2 migration and trapping and the long-term fit, but also allows us to combine the real-world monitoring data with the models to achieve the best possible results of these models and to the best forecasts for the future, and allows for a reasonable management of storage sites. So the approach of reservoir simulation is to numerically simulate the process of CO2 injection into the reservoirs by solving the mass conservation equations and by considering the various physical interactions between the phases, the porous medium, and various physical effects such as capillarity. So, but this problem of simulating CO2 storage is a complex one, and it's a difficult task, mainly because the flow problem is a multi-phase problem, mainly CO2 and saline water that usually exists underground. The problem is also a multi-physics problem because we are solving for flow and transport at the same time, and we are solving for these PDEs that are coupled together, and at the same time, they are highly nonlinear. This is due mainly to the highly nonlinear fluid behavior, which could also be a function of the saturation and the pressure itself. On top of that, the geological heterogeneity underground is a multi-scale heterogeneity where you have at smaller scales voids, and then at a larger scale bugs and fractures, which also exist at varying scales from centimeters to kilometers. So due to this high heterogeneity of the underground and the multi-scale nature of it, we need high-resolution models to capture the fine-scale geological features and processes. On top of all that, we need to account for the various geochemical reactions that occur underground for the CO2 and the minerals underground and the water, which contribute to the long-term trapping of CO2. So, to even add more insult to injury, this problem is plagued with uncertainty because of mainly geological uncertainty. Since we don't have direct observation of the underground, we only have observations from sparse data, which is usually collected from wells that are scattered through a large area of the reservoir. And not only that, the observations are scattered, and we need to account for the uncertainty in the measurements themselves. So we resort to stochastic modeling, which means we need to create a large number of realizations to quantify this uncertainty in the measurements and from the underground. The last challenge for us is to integrate the real-time data that we collect from the reservoir throughout the reservoir life and continuously update the reservoir model that we created. And we need to continuously refine this model in an iterative process that occurs every maybe 3 or 6 months with the new data to make sure that the model performs just like the reservoir actually performs in nature. This is, of course, a daunting task, and it has a compound of challenges, increasing complexity of the simulation task. The simulation task, as it becomes more complex, becomes more computationally intensive and lead to more and more extended simulation times. This affects the timely decision-making, especially in scenarios where swift model updates are crucial for operational or safety adjustments. So when everything is fine, timely simulations are not that important, but we really need them when we are at the risk of maybe a leakage or something like that. So we need timely intervention to avoid the leakage, for example. And that's when reservoir simulation comes in to help us manage the storage site effectively. So how do we manage this computational complexity and the high computational demand? The obvious answer that has been around for a few decades now is more high performance computing, more and more powerful CPUs and GPUs, parallel computing, and so on. Now, even if we assume that we have the most powerful HPC in the world, still that does not solve the problem of the iterative model update and the incorporation of real data into the physics model or the numerical model. And one of the main methods that's been used for decades as well is surrogate models. These surrogate models can address the high computational intensity of the task due to the stochastic nature of the problem by creating these simplified models that represent as much of the physics of the problem as possible. But of course, when you discard some of the physics of the problem, you are sacrificing some of the accuracy. And balancing these two is very tricky. In more recent years, machine learning surrogates have gained a popularity because they address some of these problems and they allow us to incorporate real-world data easily into these surrogates. And some of these approaches, such as pins, allows you to incorporate both pins and the measurements from the real-world, real-time measurements. However, something like the data-driven neural networks, which are just simply regression models, or the PENS approach are simply solve one instance of the PDE. On the contrary, if you look at neural operators, which are the main topic of this talk, they solve a parametric PDE. So you can generalize over a wide range of parameters, and you can actually solve the problem of computational complexity once you train a model, and you can achieve fast model updates and fast results using neural operators. There are many other approaches, but we believe that the most promising one is neural operators. Now, let's move on to the problem setup. The simulation is done. We solve the problem of the mass accumulation equation for multi-component flow problem involving CO2 and formation water. And the equation of mass accumulation is written for each component eta. You can see here on the left-hand side, we have the temporal derivative, and on the right-hand side, we have the divergence of the advective and diffusive mass fluxes. And then we have the source term. And of course, as we said, this equation is written per component eta. Now, for the diffusive term, we actually discard it from the equation, and instead we rely on the numerical errors and the diffusion from the numerical discretization as a result of the discretization of the equation. And for the advective term, we solve it using the Darcy equation, also per component eta. And this term is the advective mass flux that gives us the pressure buildup, which is the second dependent parameter that we try to solve for, the first one being the saturation. So this is the Darcy equation. And these two equations are coupled through the capillary pressure, and which compounds you can see here some of the reasons for the nonlinearity, because the capillary pressure itself is a function of the saturation. So for training the various architectures that we are gonna discuss in this paper, we use an open source data set published by Win in 2022. It's actually, this paper is the same paper for the UFNO. So the data set was first published and tested on the architecture in the same paper, on the UFNO architecture in the same paper. The data set consists of 5,500 realizations, so it's quite comprehensive. It contains 4,500 realizations for training and 500 realizations for validation and testing. By realization here, we mean one instance of the PDE where the parameters vary from one realization to another. The dataset contains two outputs. These are the dependent variables, which are the gas saturation and the pressure buildup. We are trying to learn to predict them. And 10 inputs. These include 4 field variables, and the remaining 6 variables are scalar variables. This is an example from the dataset. In the field inputs, we can see, for example, the horizontal permeability field, the vertical permeability field, and the porosity map. And here you have the scalar inputs. Additional to the field inputs, you have the well location and the perforation length. These combination of inputs, we are trying to map these inputs to the output space for the gas saturation, which is, as you can see here, and for one example, where we have 24 time snapshots for the solution, starting from 37 days up to, it actually starts at 1 day up to 30 years, and the same for the pressure. In these panels, you can see an example of this. Of course, for every realization, the horizontal and these input parameters change, and the solution subsequently changes. So as we said, the dataset contains 24 gradually coarsening time snapshots ranging from 1 day up to 30 years. The actual spatial itself is 2D spatially. In the thickness of the reservoir of these reservoirs or realizations varies between 12.5 meters up to 200 meters, while having a constant grid thickness, meaning that some of these reservoirs might have a smaller number of vertical grids than others. And to account for this, the dataset uses zero padding to make sure that all realizations are consistent in the spatial resolution, and each snapshot contains 96 by 200 grids. So in this dataset, supercritical CO2 is injected at a constant rate into a radially symmetrical reservoir, 2D, meaning that's 2D, through a vertical injection well with a radius of 0.1 meters. The CO2 injection is simulated for 30 years at a constant rate ranging from 0.2 to 2 metric tons per year, and this value is constant per realization. The radius of the reservoir is 100,000 meters, and the system is solved using the numerical simulator Eclipse E300, a finite difference method with upstream weighing for spatial discretization, and the adaptive implicit method for temporal discretization was used to solve the system of equations. The input and output shapes are summarized here. So now I would like to move on to neural operator learning. I'm pretty sure many of the people in attendance here are experts, but I still would like to introduce it to the uninitiated. So in machine learning context, operators are infinite dimensional space mappings between finite function spaces. And we would like to learn an operator that approximate this operator G that maps U, the input space, to the G of U, which is the output space. Most existing approaches, as we discussed earlier, such as the finite difference or the finite element, our traditional machine learning approaches, even PINs, aim to learn a single instance of the PDE, while operator learning methods try to learn a parametric PDE, meaning that it can generalize to as many instances of the PDE. And the idea here is that once a model is trained, it can generalize to new input functions, and the inference time is very small. So it's we offload all that solution time in the training, and in testing, it's really fast. It's usually in orders of magnitude faster than a traditional numerical solver. This is because for every new instance of the PDE, we need to run the numerical solver again from scratch. While with the operator learning, it already learned how to map to this new solution given the new input. So this is an example from another paper that we worked on that shows you the space of input functions. This example is for the Buckley-Leverett problem. The space of input functions would, for example, include the flux functions, and we want to mapping the space of solutions, which is the spatiotemporal solution map. And we map between these, and given a new flux function, we can get the new solution given that the operator was trained well to predict reliably. So these are some of the neural operators that we will discuss in this paper, in this presentation. We will first start with the Fourier neural operator because the UFNO was built on top of the FNO. So the next operator we will discuss is the unit enhanced Fourier neural operator, the UFNO. Then we'll move on to the original operator learning algorithm, the DeepONet, and then the multiple input operator network, Udonet, which is an extension of the DeepONet. And then for the Fourier enhanced multiple input neural operator, which is a unique architecture that combines both the Udonet and the Fourier neural operator. And finally, we will reach the U-Net enhanced operator network, which we termed the U-DeepONet and introduced for the first time in this talk. So the reason I highlighted these three in blue, that the UFNO and the Fourier MIONet and U-DeepONet all have been benchmarked on the same data set that I described earlier. And this allows us to easily compare between the three architecture and contrast the different attributes and benefits of using a specific architecture. So I'm sure many of you are familiar with this picture. This is the FNO architecture, which is basically A of X is the input. You have a shallow neural network to map to a higher dimensional channel space. And then you have the Fourier blocks. In the Fourier blocks, you have the Fourier transform, a weight matrix called R that learns the Fourier that helps train the Fourier. And then you have the Fourier inverse Fourier transform, and you have an additional weight matrix. Then the sum of these two is passed through an activation function. You build these Fourier blocks consecutively, and then you have the Q, which is also another shallow neural networks that maps the Fourier output to the solution space. So the FNO is formulates the operator by parameterizing the integral kernel directly in Fourier space, and the parameters of the network are defined and learned in the Fourier space. The coefficient corresponding to the Fourier series representation of the output function are inferred from the data set. So this is referring to the R and W matrix that are trainable tensors. That contains the weights, the trainable weights. The problem with the FNO, in our opinion, that it contains a large number of trainable parameters. These trainable weight tensors, R and W, are you have an R and W tensor in each Fourier block. And if you have a large number of blocks, then you have a very large number of trainable tensors, as we will see in this talk. Then when in 2022 introduced the UFNO, which is a variation of the FNO, in which in some of the Fourier blocks, the UNet block is included. So in this, the main difference here, as you can see, that the output here this is the output of the Fourier block, and this is the output of the UFNO block, which includes the UNet. The UFNO, the issue of the UFNO that it has an even larger number of trainable parameters, because you have now 3 trainable weight matrices in the UFNO block. And if you maintain some Fourier blocks, you have 2 weight matrices, R and W. So, and these, of course, compound as if you have more and more layers, you have more and more trainable parameters. On top of that, the size of the weight tensor R grows exponentially with the increase in the number of Fourier modes. This, I mean by this, is that if you have a 2D or a 3D data set, it means you'll have a 2D or 3D tensor, and it grows exponentially, which probably suggests that the UFNO or the FNO suffers from the curse of dimensionality. The U Fourier layer also is very expensive to compute if the input data is 3D. This is a different reason, since if you have the input data is in 3D, you will have to resort to a 3D convolution in the UNet, which is also very expensive to compute and hard to scale to even higher dimensions, which even becomes more expensive. So on top of that, the FNO loses the resolution invariance in time, meaning that you cannot make predictions at time steps that you haven't trained on. This is specific for the UFNO due to the presence of the UNet in the U Fourier blocks. Now we move on to the DeepONet. The DeepONet was the first operator learning architecture introduced in 2019 by Lulu and others, I believe from Brown. And when we usually talk about the DeepONet, we are referring to the unstacked architecture of the DeepONet, where all the input functions are processed through one branch and mapped to a representation that we will call B. And then the spatiotemporal coordinates are processed through the trunk and mapped to T. The cross product of the branches, the branch and the trunk gives us the operator learning that we are aiming to achieve. Some of the features of the DeepONet, specifically the unstacked DeepONet architecture, that it's a high-level framework in which the architecture of the trunk and the branch network is not restricted to any specific kind of network. Although it was initially introduced with the feed-forward neural network, the authors mentioned that you can use any type of neural network if you see fit. And we make use of this advantage of the DeepONet to use the U-DeepONet in the branch and to use the unit blocks in the branch of the U-DeepONet and introduce the U-DeepONet for this because our input data is mapped into a grid. On top of that, the DeepONet is also grounded in the universal approximation theorem of operators. We mentioned this. The input domain, one of the other advantages of the operator, the DeepONet, that the input domain is different from the output domain, meaning that the output of the DeepONet does not to be discretized on the same mesh as the input. This is in contrary to the FNO. Another variation, an important variation of the DeepONet is what is called the multiple input operator net, which we call the MIONet. In this architecture, the authors, Jen and others in 2022, showed that you can use multiple branches and a single trunk combined through an element-wise product to learn multiple operators simultaneously. Now, the Fourier MIONet architecture introduced by Jiang in 2023 takes advantage of the MIONet architecture. So they use multiple branches to process the different types of data in the CO2 sequestration data sets. They have a branch for the field inputs, and they have another branch for the scalar inputs, although here they use a sum instead of the dot product that was introduced initially for the MIONet. Then they pass the output of the MIONet to the Fourier to the UFNO actually. So this architecture is a hybrid between the MIONet or the DeepONet and the FNO or the UFNO, if you wish to call it. So it's a hybrid architecture, and one of the ideas that we postulate for the U-DeepONet that it's unnecessary to do this because both of these, or each of them on its own, is an operator learning algorithm. So using both of them in a single architecture might be redundant. And we will see why is that in the results of the U-DeepONet. So the goal of the Fourier MIUNet architecture is to tackle the three main weaknesses of the UFNO, namely the computational expense associated with the use of the 3D convolution. Since they separate the temporal dimension in the trunk, they now don't have to do a 3D convolution in the UNet here. This is also true for the number of Fourier modes. So the R matrix is no longer a 3D matrix now. It's a 2D matrix, which substantially reduces the number of parameters in the overall model compared to the UFNO. They also want to regain the resolution invariance imposed on the time dimension by the UNet, since the time dimension is no longer processed with the in the UNet blocks, in the UFNO blocks. Now we move on to introducing the U-DeepONet architecture, which is quite frankly a simple architecture, and it's a culmination of some of the good ideas that we have discussed so far. So we use the DeepONet, and we take advantage of its flexibility of using any type of network in the branch or the trunk. For the trunk, we retain a simple feed-forward neural network. In the branch, however, we include first a single layer, we call it P, that maps the input space to a higher dimensional space, so you can increase the number of channels. Then we pass that to the UNet. The UNet block here is the same as the UNet block used in the previous two architectures that utilized the UNet. And then we pass that output through an activation function. And you do that recursively. So in the paper, in the presentation today, we'll have through 3 UNets. So once you pass the output of the P to the UNet, then through an activation, you pass it again through a UNet and then an activation. You take that output and you do the cross product to get the output of the DeepONet. Now we want to map the output back to the input space, to the solution space. We chose to use a shallow neural network to do that mapping. We can use the sum as was originally proposed, but we found that using a shallow neural network resulted in a slightly more accurate results, and it's a computationally cheap way of achieving that. So this is the algorithm. As we mentioned already, we left the inputs to a higher dimensional representation using a linear layer P, and then we apply L number of units iteratively, followed by an activation function. The trunk is a simple feed-forward neural network. Then we perform the product of these two outputs of the branch and the trunk, and we project back to the using a shallow neural network to the solution space. You can also opt to use the sum over the features of the output to map back to the solution space. So our main proposition here is that it's unnecessary to process the inputs through Fourier layers. We will show that only using the units without the Fourier layers and its associated weight matrices, we can achieve similar or even better results. We use the unit blocks in the branch of the DeepONet to process both field and scalar inputs, so no need to separate them. It doesn't have that computational significance. And because we separate, just like in the MIUNet, we separate the time into the trunk and we process it separately, we can use 2D convolution in the unit and get rid of the 3D convolution, which is quite expensive to compute and the train. So this setup also allows for multiple input operator learning without using the MIUNet, as I already mentioned. For the specific case that we will be working with, this is the architecture that we chose to use. We have the inputs, and then we pad the inputs with zeros. We pad the spatial resolution only. And then we have the trunk input and the branch input. Here we separated the time variable from the other input variables. We have 10 layers in the trunk network, and we have an activation function. We can choose any activation function in our testing. Any popular activation function, such as the ReLU or the TAN-H, works very well. In the branch network, we have the P lifting layer that maps to a higher dimensional space. And then we have a unit, 3 units with activation functions. And then here you have the outputs of both the branch and the trunk. We perform the dot product between them. And then we project using a shallow neural network of 2 layers to the solution space. Here, the 64 is the number of channels. So we start off with 12 and we map to 64. I know I mentioned earlier that we have 10 input parameters, but the two additional parameters are the X and Y, the spatial grid of the spatial grid. And we did this to stay consistent with the results of the UFNO and the MIONet. Many papers in the literature showed that including the grid into the input of the Fourier or the FNO Fourier neural operator improves the accuracy. We know that this is not necessarily for the DeepONet, but we wanted to just be consistent with the other two papers, and that's also the reason why we chose the same unit architecture in our U-DeepONet as the other two papers, because we want to make as little variation as possible, apart from using a DeepONet, obviously, and to be able, in order to be able to make good comparison and reliable and fair comparisons with the other two architectures. So in this case, this is for the saturation case. We chose to map the features into 64 features. You can choose any number. Larger numbers result in more accurate solutions, but they are also more expensive. So we chose 64. We found it to be suitable. We use for the saturation a sine activation function, which is not a typical choice, but we found it to be slightly more accurate than using a ReLU or a tan-H. And for the projection layer, we use the ReLU. In the pressure model, we train two separate models for the saturation and the pressure buildup. In the pressure buildup model, we use the ReLU activation functions, and we use 96 channels. We map into 96 channels instead of 64. For the loss function, we use the L2 loss function in addition to the first derivative term, which has been shown to greatly improve the prediction accuracy and promote faster convergence, especially in discretized problems. This is the same loss function that has been used in the UFNO and the MIONet, Fourier MIONet architectures for the same data set. And as I mentioned, we train two separate U-DeepONets for the saturation and pressure buildup, and we maintain the same hyperparameters as the other two papers for as fair a comparison as possible. If you want more details about the hyperparameters, you can refer back to the paper. So for testing, we use the testing set, which I remind you contains 500 realizations. For testing the saturation, we use 3 metrics: the plume area coefficient of determination, which is the plume area R square, the plume mean absolute error, and the mean absolute error. The plume area is defined as the non-zero values in either the ground truth or the prediction. This is specific for the saturation model because the saturation outside the plume area is 0, and it may contribute by reducing the error in a non-real way. As for the pressure buildup, we also use 3 metrics. We use the R square score. We use the field mean relative error, which is the mean absolute error between the reference solution and the predicted solution at each time step, normalized by the difference between the maximum and minimum pressure at that specific time step. We also use the mean absolute error. Now, let's look at some of the results. Here in this table, we summarize the most important results for the saturation model, and we will compare the UFNO, the Fourier MIONet, and the U-DeepONet. The first thing that I would like to compare is the number of trainable parameters. We can see here that the UFNO, as proposed by the authors, Wynn and others in 2023, contains about 33 million trainable parameters. The Fourier MIONet managed to drop that to about 3.6 million trainable parameters. In our case, the the U-DeepONet for the saturation model only contains 1.8 million trainable parameters. This is reflected in the GPU memory usage, where we have about third the memory usage for the U-DeepONet compared to the UFNO. This is important because most commercial GPUs are within the range of 8 GPUs in terms of RAM. So if you have a very large model, it might be difficult for some people to train it. And that's what this is one of the features of the U-DeepONet, that it is a very light model. And this contributes to a very low training time per epoch. As you can see here, the UFNO takes about 2,000 seconds per epoch to train, while the Fourier MIONet takes about 730, and the U-DeepONet only takes about 100 seconds to train. So when comparing, we use V100, NVIDIA V100 for both the UFNO and the U-DeepONet. For the Fourier MIONet, we don't have access to their code. They report this number using an NVIDIA GeForce RTX 3090. And as you may know, this GPU has about twice the tensor cores as the V100. So it's a substantially more faster GPU, yet the U-DeepONet is significantly faster in training compared to both the UFNO and the Fourier MIONet. So this contributes to the final or the total training time, where the UFNO for the saturation dataset takes about 53 hours, again on the V100 GPU. The U-DeepONet only takes about 3 hours to train. This is about 20 times fold increase in speed. The Fourier MIONet again run on a 3090 GPU, takes about 15 to 18 hours, maybe 15 to 18 hours to train. So this constitutes a substantial improvement in training speed compared to the other architectures. Not only that, but the accuracy is also substantially improved compared to the other architectures. We can see from the R-score here that the U-DeepONet is more accurate than both models. And so in the R-score, higher is better. In the mean plume error and the mean absolute error, lower is better. So in terms of the mean plume error, the U-DeepONet is more accurate than the UFNO. It wasn't reported for the Fourier MIONet. And in terms of the mean absolute error, the U-DeepONet has about half the mean absolute error of the Fourier MIONet, meaning that is twice as accurate and also more accurate than the UFNO. So not only is it much faster in training, it's also faster in inference, and it's more accurate. Now, let's look at some results from the saturation. Here we have two cases. We plot them at 2-time snapshots at 7.3 years and 30 years. And we can see here the reference solution in the first panel. Then the panel below it, we have the U-DeepONet. And here is the mean absolute error. Below that, we have the UFNO solution and the mean absolute error. This is the second case. And we have two more cases here. One thing to note here, and it's a testament for the dataset that was produced by Wen, is that the dataset is very rich and it has a wide range of scenarios for CO2 sequestration, plume behavior, which we believe is very good. And this dataset, we encourage people to use it to benchmark their models. And we think that such a dataset and such a rich dataset can actually help move the field forward, as we can all refer back to it and benchmark our models and our methods and track how we are improving over time. Now we'll move on to the pressure buildup model. And here we needed to use a slightly bigger model with 96 channels, as I mentioned earlier. The UFNO maintains the same number of trainable parameters of 33 million. The U-DeepONet has only 4 million. It's reflected in the GPU memory usage. The training time as well is the U-DeepONet takes only about 125 seconds compared to 2,000 seconds for the UFNO, which is reflected in the total training time. 75% 5 hours is just too much. It was too much for us. It was one of the primary reasons we actually worked to produce a new architecture that is significantly more efficient. Because if you want to wait 75 hours for one run, it's just going to delay any development that you're doing. So a U-DeepONet that can run in under 5 hours is we believe is a substantial improvement. Now, if we look at the R-score, the U-DeepONet is more accurate in terms of the mean relative error. Actually, the UFNO surpasses the U-DeepONet in terms of performance, but it's a slight win for them. And for the mean absolute error, the U-DeepONet is also more accurate. So in 2 out of 3 metrics, the U-DeepONet is more accurate. And this is also reflected in the inference time. The U-DeepONet is faster in inference time. We don't have much information about the performance metrics of the Fourier MIONet because it was not reported in the paper. These are some of the visualized solutions for the U-DeepONet and the UFNO and the mean relative error reported here. We have 4 cases. Again, we can see a diverse collection of behaviors for the pressure buildup. Now we want to examine the data efficiency of the various of the UFNO versus the U-DeepONet, which we just introduced. For the gas saturation, we here have the mean plume error and the number of training samples. So we vary the number of training samples and measure the mean plume error on the testing dataset. We subsample the training dataset randomly, and we vary it between the maximum of 4,500 up to only 500 realizations included in the training. We also vary the batch size to see how does it affect the performance accuracy. And as you can see here, the U-DeepONet not only is more accurate with the full data set, it's consistently more accurate throughout. On top of that, if you compare these 2 data points, so the U-DeepONet maintains the same level of accuracy and is even more accurate using a batch size of 6 compared to the UFNO with the full data set. This tells us that the U-DeepONet is much more effective at learning and is better at generalization. Now, for the pressure buildup, we do not see the same improvement in performance. Also, we have some improvement in performance in the small data regime here. But this is, we believe, because the UFNO is well suited to learn diffusive PDEs. And it has an advantage in such case since it uses the Fourier transform, which is very good with working with smooth PDEs such as the pressure equation, which is diffusive by nature. Now we want to look at the inference at unseen time steps, and we have here the blue line where we have the original full data set, meaning that all time snapshots are included in the training. And if you see a halo square, it means that this time snapshot was not included in the training. And of course, our reference solution is the blue line. We report the mean plume error. This is for the gas saturation case. We see here that the gray line reflects the same exact architecture that we have been examining so far for the U-DeepONet. And we can see that the U-DeepONet can usually generalize very well and maintains its accuracy when generalizing to unseen time steps. These are the halo squares here. Now, we weren't very satisfied with this performance because we lose some accuracy at some of these unseen time steps. So we decided to fine-tune the trunk network. So we changed the architecture from 10 layers to 16 layers, and we changed the width from 64 layers to 64 neurons per layer to 14 neurons per layer. And that resulted in a significant improvement in generalization performance to unseen time steps. This is represented by the orange line, and we can see that it can generalize very well and it maintains its accuracy throughout, apart from this very first unseen time snapshot. This is because the change in the saturation plume early on is very rapid, and it's very difficult to generalize to that behavior. So this is the solution at day 1, this is the solution at day 2, but this is the solution at year 30. So the change here is much smoother and much smoother compared to here. Here it's much more rapid, and that's why it's very difficult to generalize. Nonetheless, the error is not that bad at this time step, and it's the only time step that it doesn't perform as well as expected. In all other time steps, the mean plume error is essentially exactly the same compared to a training data set that includes all time snapshots in the training. One more thing to keep in mind here is that if we can reduce the size of the training data set by half, by removing half of the time snapshots, we can also achieve a much higher, much faster training time. So this model takes about an hour and something to train, and at the same time, it's maintaining its accuracy apart from the second time snapshot. So this is one more thing to keep in mind. Now we do the same for the pressure buildup, and we see that the performance is not as good as expected, although if you look at the scale of the y-axis, it's not that bad at all for the same architecture used earlier when we compared the gray line with the blue line at the unseen time snapshots. But we also fine-tune the trunk network for the pressure buildup model in the same way, meaning changing from the depth from 10 layers to 16 layers and changing the width from 96 to 16 neurons per layer. And we see that it improves the generalization to unseen time steps considerably. And here we report the average mean relative error across all time snapshots, and we see that the orange line is very close to the blue line that includes all time snapshots, although this one only has half the time snapshots included in the training. This brings me to the conclusion of the talk. So to conclude, the U-DeepONet architecture outperforms the UFNO and the MIONet in training and testing for multi-phase flow problem and transport in porous media. It's up to 20 times faster than the UFNO, more than 5 times faster than the MIONet, although it's running on a much faster GPU, but we couldn't replicate the results because the code is not available. It's more accurate and faster in testing. It's more data efficient. It requires about a third of the GPU memory usage. It can generalize well to unseen time steps, and the U-DeepONet can learn multiple operators simultaneously without the use of the MIONet. These are some of the references that were included in the talk. And thank you very much for attending. I'll be happy to take any questions.
Thank you so much, Vali, for your great talk. Now we open the floor for questions. Are there any questions for the speaker from the audience? I think Vivek wants to ask a question. Vivek, can you introduce yourself first and then ask your question?
Waleed, great talk. My name is Vivek, and I'm a PhD student working with Professor George Karniadakis. A great talk, by the way. I have a few questions. So,
Please.
Can you go to the slide in which you were describing the loss terms? I think this slide. So I wanted to know how you computed the partial y hat by partial r. If I understand correctly, you would have probably used a finite difference stencil and convolved it over space. Is that what you did?
Exactly. We pre-computed in the training loop.
Yes. So you would be having like a layer that convolves a predefined stencil in space.
Yes,
and
exactly.
So that term will be sensitive to the resolution, which is, I guess, 106 or 90,106 in your case. It will be dependent, it will be sensitive to the resolution, right?
Yes, so it has the same resolution as the solution, right? 96 by 200.
Correct. So I have a question.
To be honest, in our testing, although this is reported in the literature for multiple papers, it doesn't make that big of a difference.
Yes, that's what I want to ask.
It improves, certainly improves, but in our U-DeepONet, it wasn't that significant.
All right. What is the value? Sorry, go ahead.
Yeah, go ahead, please.
What was the value of the beta you have played with? or you
Half.
have find?
We didn't really play with it. It was for UFNO paper and the MIO net paper. They used half, and we stayed with it. As I mentioned earlier, we really tried not to change as many things as we can, so that it's a fair comparison. Although there are a lot of things we can do to even further improve the results, but we thought this is enough. And with as little changes as possible, just changing the architecture itself, it's enough to show that that U-DeepONet outperforms significantly the UFNO.
Okay. Thank you for answering the question. I have one more
No.
question.
Mhm.
Regarding the architecture, you said you are using multiple units. So have you tried using, or why did you choose the number 3? Have you tried just 1 unit, 2, 3, and you
Yeah,
found
of
it?
course. You can
Yeah.
use only a single unit. It
Yes.
will the accuracy will deteriorate a little bit, and you will gain a lot in efficiency. So
Okay.
you have to balance these two. If you add, we tried even 4 and 5 layers, you will improve a little bit in the accuracy, but then the
It dies.
improvement in it's
Actually,
diminishing returns. That it's not
right, right.
justified compared to the
I
computational
understand.
expense associated with more units.
And within the unit, you should be having some nonlinear activation functions, right?
Yeah. We
Or
use the leaky ReLU.
literally within the unit, and outside the unit also you put the additional activation layer. Yes.
Yeah, so outside the unit for the saturation, we chose to use the sine actually. Although you can use the tan edge, is slightly better, especially
Okay.
at the end. It doesn't saturate, so the loss doesn't saturate as you reach as much when you reach the 100 epochs. Again,
Okay.
by the way, the choice of 100 epochs, we made it just to stay consistent with the other papers.
Yes, I
And
understand.
using the sign, and specifically in this case, if you use a higher number of channels, if you map to instead of 64, 96 or 128, and you use a sign, you actually can improve the accuracies quite significantly.
All
But
right.
we choose not to do that, just to stay consistent with the others.
Okay. Thank you. Thank you for answering my
Uh-huh.
questions, and great talk. Great work.
Yeah. Thanks, Vivek.
Okay, Omar Wahid, can you first introduce yourself, please, and then ask the question?
Sure, yeah. Hi, everyone. I'm Umair bin Wahid from King Fahd University. Thank you, Waleed. That was an excellent talk and very comprehensive. So I have a couple of questions regarding your slides when you were showing about prediction for unseen time steps, right? So you can think of this as an interpolation example, but you did a good job of comparing the other methods, throughout your presentation, but not here, right? Did you look at how the other methods perform at unseen time steps?
That's a very good question. For the UFNO, they state in the paper that they cannot do this to start with. So I can bring you a quote from the paper that the UFNO cannot generalize at all to unseen time steps. In the MIONet paper, they actually show that you have these spikes, but much worse for the UFNO at unseen time steps. And for the MIONet paper, actually, the results are quite confusing to me, at least. So I didn't want to compare now. I wanted to wait for the journal paper or an updated archive paper to compare with them. So I wanted to be fair to them because I have some I'm a little bit skeptical about the results, and they are not being consistent with reporting the results, especially in this section. And you saw they did a very good job reporting the results up to the saturation model. But then, as you saw here in the pressure model, there are a lot of missing information. And then the inference at unseen time steps is the section after that, and you have more and more missing information. So I just didn't want to do the comparison at all at this point.
I understand. And you mentioned about
Sorry,
UFNO.
one more point I just remembered. One other reason is that we are already much more accurate in both the pressure and the saturation. The U-DeepONet is already much more accurate compared to the Fourier MIONet. And we didn't lose as much accuracy as I showed here. So you went from 1.67 to 1.75. So my prediction is even with this 1.75 is more accurate than their model with the full temporal with all the time snapshots. It's already more accurate. And this is, by the way, I forgot to mention this. This is not even using the full data set. We are using only 3,500 realizations to train, because we already showed that we can maintain the accuracy with much less realization in training. So not only we removed half of the data set in terms of number of time snapshots, we also reduced the overall size of the training data set. So this takes about an hour to train only.
Yeah, thanks, Waleed. Just to follow up on your answer, you mentioned that UFNO folks said that they cannot generalize at unseen time steps, right? But probably you implemented their code yourself. So what did you see yourself? That was my question.
I actually didn't have to implement it. They actually published their code. And
see.
as I mentioned, the second paper, the Fourier MIONet, they included some results from the Fourier, from the UFNO.
Right.
And they showed in their results that they have large spikes at every unseen time step. So you'll have a spike similar, even worse than this one, at everywhere, at all the unseen time steps. That's for the UFNO. So they did that. So I don't have to do it.
Yeah. And in terms of extrapolation beyond certain time period, I think you made a comment that even if you train for half, the time, then because the solution stays does not change much, your method does not give large errors, right?
No,
Is it?
this is not quite accurate. Maybe I wasn't clear when I mentioned this. No, we cannot extrapolate at all. So if you notice here, we include the last two time steps in the training, because if you see how we did it, is that we pick the first one and then we skip one. We always skip one. If we did that all the way, we will have to leave the last one out out of the training data set. If we did that, the error will shoot up to 10%.
I see.
So we cannot actually extrapolate at all. This is one of the disadvantages of this model. So meaning we cannot extrapolate is that the error is very high when you extrapolate. And this is something we are working on in a new architecture. Hopefully soon will be out to address this issue of extrapolation.
Great, great. Thank you, Waleed. That was an excellent talk. Thank you so much.
You're welcome. Thanks, Amir.
Are there any other questions?
Hey, I have a suggestion for you, Waleed. So,
Please.
since you are having discussion with Dr. Umair about temporal extrapolation and improving the temporal interpolation, we have worked something similar in our group. So, the technique is called, we worked on a paper called DITTO, which is diffusion-inspired temporal transformer operator.
I'm familiar.
Yeah, great, thank you. So, here we
I'm
use a
familiar with
unit. Yes, the kind of operation you're doing at the end of unit 3 times iteratively, we are doing at different levels. And additionally, we have attention blocks in between. So in one of the section, we try to address the difficulty of temporal extrapolation in data-driven modeling. So please refer figure 2 in our work. I have put the link. So this is model agnostic. So I believe even with the U-DeepONet enhanced DeepONet, if you slightly change your training strategy, you would be able to achieve not only interpolation, but also you would be able to do a good job in extrapolation. If I understand correctly.
I promise you, I'm working on this specifically, the things that you mentioned, and I'm well aware of the DETO paper. I'm actually following your work and Dr. Umair's work. So I've read your recent papers and I'm well aware of what you guys are doing.
I have one more suggestion for you. Also go through a person named Dr. Johannes Brandsetter's work. I think he was the first person to mention about the temporal bundling for data-driven modeling.
This is something I'm not familiar.
Or let me just type it out to you.
Oh, please. That would be perfect. I don't think I'm familiar. Do you recall the title?
Probably you will have to go through message passing neural PDs. Maybe Alan can correct me. I think that's the paper. But go through his papers. He has definitely worked on temporal bundling training strategies. He has done a lot more work than this is just the basic idea. If you go through his works, he does something to backpropagation also to improve this. So I'm sure
back
you find these
propagation through
papers.
time, probably.
Okay, it's PDEs. My bad.
No,
Yeah.
it's okay. It's all right. So I think you're referring to back propagation through time.
Yeah, he has done some work. You should definitely go through some of his works. That
I
will
might
help.
have seen that paper. I'll take a look to see what Dr.
Yeah.
Johannes is doing. Yeah, but
Yeah.
this is actually the main challenge for the U-DeepONet at the moment is temporal extrapolation, and this is something we are looking into at the moment as we
Yeah.
as we speak. This is something I'm looking into, and
Yeah.
hopefully the next web paper will be addressing that. We have some ideas as well.
Great. All the best. Thank you.
Thanks for the suggestions, Vivek. Thank you very much.
Bye.
Walid, if I may just ask you
Please.
one more thing here. Since we were talking about temporal extrapolation, have you tried to, add physics here in the training? Which you haven't right now, right? It's just data-driven.
Yeah, so we haven't tried that so far, and it's an obvious solution, right? So if you include the physics, we know that physics-informed models usually extrapolate well in time. So this is something that we are thinking of to do down the line, but this is the obvious answer, and it's the more difficult to implement and the more difficult one to do, actually. So we wanted to see if we can find a machine learning-based solution. And then you can always do the physics-informed solution. And hopefully it works. I don't think I've seen any papers with physics-informed operators on heterogeneous data. Have you?
I think Sifan has a paper on this.
But not on I've seen Sifan's papers, but they are not on heterogeneous data set, heterogeneous domains. That's the real challenge with physics-informed.
So we implemented this in our enriched DeepONet paper, physics-informed DeepONet as well, with heterogeneous medium. I'm not sure we faced much challenge with that, but we can discuss offline.
So the kind of heterogeneity we are working with is with the permeability map and the input and the output, and so it's a special kind of challenge. Maybe there are some solutions out there that I'm not aware of, but it's quite a challenge. And maybe we'll try to do that down the line. But yeah, I'll be happy to take that discussion offline with you. Just hit me up on LinkedIn. We already talked before.
Are there any other questions from the audience?
Okay, seems that's it.
Yeah. So
Okay.
I think, yeah, we don't have any more questions. Thank you so much for your great talk and joining us today. It's time to close the session. Thank you, everybody, for joining us today. Have a great weekend.
Thank you, Nazanin, and thank Dr. George for me as well. Thanks for the invitation, and I really appreciate the discussion with Umer and Vivek. I hope to do this again in the future. Thanks. See you.
Good luck.
Bye.